Okay, so let's take another example. Let's take a look at number 18 here. And I want you to look, this is what's called a rational function. By rational, it doesn't mean it behaves particularly rationally. What that means is, think back to your elementary school years in math, and what you did was you started with your counting numbers, right? The natural numbers, 1, 3, 1, 2, 3, 4, 5, 6, 7, blah, blah, blah. And you added them, you subtracted them, and then you divided them. So you get things like 3 over 5. Well, we call those rational numbers. If a fraction, it can be written as an integer divided by an integer. It's by definition something we call rational. Versus if you can't write it like that, for example, square root of 2, there's no fraction where you could write it exactly. And in algebra, what we say is if I have a polynomial divided by a polynomial, we call that a rational function. So we're replacing the concept of an integer with the concept of a polynomial. And downstairs, the same thing. Now I want you to take a look at the denominator. If x is equal to 3, bingo, we got a problem. Because this is going to be 0. But notice if I put in a 3 here and I square it, I get a 9. So we get 9 minus 9, which is 0, divided by 0. So we are dividing by 0, which we do not want to do. So let's go back to our idea of the following. So let's go back to Zeno's paradox. Remember the problem that if I want to walk 1 mile, I have to walk a half a mile. And then I have to walk a half of the remaining mile, which is a quarter. And then I have to walk half of a half, which is an eighth of a mile. And their problem was you never reach the wall. And we know that that's not true. You can walk the mile. So what we do is we go back to our tables, and the problem is we had something called, when we did this, when we put it into 3, we got 0 over 0, and this is something we call the indeterminate form. And this is going to come back to us when we go to coming up with the definition of a derivative, which I'll talk about. So 0 over 0 in some cases could be 0. 0 over 0 could actually be 1. 0 over 0 could be positive infinity, or negative infinity, or the square root of 7 over 13. We don't know what it is. We have to do some extra work. So let's take a look at what happens here. If I have a problem there's a big problem at 3, because I have this 0 over 0 stuff. So what I'm going to do is I'm going to use this concept of a limit, and I'm going to approach 3 from the left and from the right. So if I'm approaching from right, so I'm going to pick x to be 3.1, 3.01, 3.001. And if I come in from the left, 2.9 for my x, 2.99, 2.999. And I just put these numbers into my function. And I'm going to get minus 5.9, minus 5.9, minus 5.999, and negative 6. It looks like these two numbers are matching up. So it looks like as we come in from the left, that's what this little negative, it doesn't mean that it's negative, it just means we're coming in from the left. If you don't like that, you could put L there, and this one could be R for right. So it looks like as we're coming in from the left to 3, the function, when I put it in, I just do the numerics here, I get negative 6 and a negative 6. That's not a proof of anything. So then the question is, how can I figure that out using algebra? And the trick is the following. The troublemaker is the 3, both in the numerator and the denominator, because we get 0 over 0, which is not good. So what I'm going to do is I'm going to play a game, and this is called long division. Now what I did was I'm just going to switch these two guys, so the negative is going to come out, And you could just check to see if this is correct, because I want to put we always write polynomials in descending powers. So if I check, if I distribute the negative here, a negative x squared, which is what we have, and a negative negative is positive. So all I did was I rearranged this, and I just pulled out a negative. Okay? Now, I'm going to come up with, I'm going to create a new polynomial called x squared minus 9. So all I'm doing is I'm taking the numerator, okay? And what I'm going to do is I'm going to do long division here in just a second. And I want you to notice that if you, right, there are no x's in this expression. So what I'm going to be looking at is 1x squared plus 0x minus the 9. If you just write this as like a 1 and a 9, $19 is not the same as $109. That's 0 is a placeholder. We're going to see that showing up here in when we get to long division. Okay, so what I'm going to do is I'm going to evaluate this polynomial at 7. Where did 7 come up? I just made it up. I chose 7 at random. Okay? Alright, so if I put in a 7, and we're just looking at we pulled out the negative. I'm just looking at this part right here. Okay? So let's take a look at something. Suppose I tell you that I have this polynomial and I evaluate it at 7. Again, where did the 7 come from? Out of thin air. So if I put in a 7 and I square it, I get a 49. I subtract off a 9, and I get a 40. Okay, keep this number in mind. What I'm going to do now is I'm going to take x minus this number, and I'm going to divide it into the polynomial. Now remember this 19 versus 109. You have to go 1x plus 0x, 1x squared plus 0x minus 9. And I write that out. That's very important, that placeholder. And I now do long division. Now some of you may have seen this, some of you may not have. So I ask myself the question, what do I have to multiply x to get an x squared? Well, that would be an x. Because x times x is x squared. So then I take this, multiply by this by this, and then I subtract. So when I take x times x, I get an x squared. When I take 7 times, excuse me, when I take x times 7, I get negative 7x. And now what we do, it's just like long division, we subtract. So this was a positive x squared, it becomes a negative. This was a negative, it becomes positive. If I've done things correctly, guess what? The x squareds cancel. And I'm left with 0x plus 7x, which is 7. Okay, so now I only have a 1-digit number, and I have a 2-digit number up here. So I bring down to 9. I ask myself the question, what do I have to multiply x by to get me a 7x? A 7. So I'm going to take 7 times this, 7 times this, and I'm going to subtract. So 7 times x is 7x. 7 times negative 7 is a negative 49. Now we subtract. This was a positive, it becomes a negative. Students usually find this a little bit easier to remember. Just put a little circle around it. This was negative, now it becomes positive. The 7x's cancel. And I'm left with 49 minus 9, which is 40, which is what I came up with by just plugging in the 7. Again, where did the 7 come from? Out of thin air. Alright? So here's what's happening. This is a very important theorem which you may or may not have seen in your algebra courses. If I give you p of x, like the x squared minus 9, is a polynomial, and I evaluate p at some constant, like the 7, I get the remainder of the long division. So what this is saying is x minus this number is, when I do the calculation, excuse me, when I put in the constant, I get a number out. And what that number is really the remainder. So if I take x minus whatever this number is and I divide it into my polynomial, I get the remainder. Now this is going to be important because if the remainder is 0, it means this factors into that. And that's what we're eventually trying to do. So let's take a look at this. So suppose now I look at my x squared minus 9 and I put in a 3. 3 squared minus 9 is in fact 0. So let's do that. What does that mean? X minus this number has to be a factor. That means it has to divide into this evenly. So let's do our long division and see what happens. Now remember, it's x minus this number. So if this were a negative 3, you'd have to go x minus a minus 3, which is x plus 3. Alright, so because the remainder is 0, it means this should go into this with a remainder of 0, which means this times this has to be this. And for those of you that are very astute, you notice that this is just the difference of two perfect squares. You could have come up with that very quickly, but I want to show you long division and the remainder theorem. So I asked myself the question, how do I make an x into an x squared? I'm going to multiply it by x. Put the x in the x column. X times x is x squared. X times negative 3 is negative 3x. Now we subtract. This was a positive, it becomes a negative. This was a negative, it becomes a positive. The x squareds cancel, and I'm left with a 3x. Now the problem is, this is a 1-digit object, and this is like 2 digits. So I bring down the 9, the negative 9. Now I ask the question, what do I have to multiply x by to give me a 3x? The answer is 3. Put it in the constant column. So 3 times x is 3x. 3 times 3 is 9. Now we subtract. Excuse me, I brought it down. 3 times x is 3x. 3 times 3 is negative 9. And notice what happens is they cancel, and I'm left with 0. That means x minus 3 times x plus 3 is this, which we know all along. Perfect square. So what this is saying is when I'm looking at, now remember I pulled out the negative and I switched these guys. So what I'm going to do is I'm going to take the numerator and I'm going to factor it, which I just did. So the factors, so x squared minus 9 factors into x minus 3 times x plus 3. So if I do that, I get, oh, isn't that cute? The x minus 3 cancels the x minus 3. No more is 0 divided by 0. Now if I put in a 3, 3 plus 3 is 6, and I have a negative, so the limit is negative 6. And that is what we saw back here. As I'm coming in from the left, I'm getting closer to negative 6. As I'm coming in from the right, I'm getting closer to negative 6. So you're going to have to be able to do this for your quizzes and tests, create tables like this. And also, you're going to have to be able to do this long division stuff. Okay, so we now have two tools. Okay, let's take another example of this long division stuff. All right, I'm just pulling a polynomial out of thin air, all right? And if we look at a graph of this guy, it looks like the graph crosses here, here, and here, So there should be what are called roots, three places where this becomes 0. And it looks like one of the places that the graph crosses is at, say, -3, at 1, and at 5. Now this is not a proof of anything, this is just an observation. So if I take a look at my graph, it looks like it crosses here at 3, at 1, and at 5, and I just put approximately. Okay? So let's see if we can verify that algebraically. Too many wires here. Oh. Okay, so what I'm going to do is if I put in a 1, my polynomial, I cube it, I square it, multiply by -3, etc., and just go through the arithmetic, I get 0. What is that telling me? The remainder of x minus 1 is a factor, because when I divide this into this stuff, I get a remainder of 0, which means this has to be a factor. Take a look at if I put in a -3. So you're going to take -3 cubed, -3 squared, -3, etc. Go through the algebra, the arithmetic, and you get 0. Which means, excuse me, x minus a -3, which is x plus 3, is a factor of this polynomial. So be very careful. If you find a number, and you evaluate your polynomial and get 0, it means x minus that number. In other words, x minus a -3 is a factor, which means this should divide into this guy. Let's do it. So, we take and we divide. So I'm going to take, remember, minus a minus is positive. So I ask myself the question, does this divide this? If it does, it means it's a remainder of 0. So I ask myself the question, what do I have to do to x to give me an x cubed? Well, if I multiply it by x squared, that would give me an x cubed. So put the x squared in the x squared column and multiply. So we are going to get x cubed plus 3x squared. And now I subtract. This was a negative, it becomes positive. This was a positive, it becomes negative. If I've done things correctly, I should have eliminated my x cubes. I have. Now, be careful, I have a -3x squared and negative, so I have a total of -6x squared. Now the problem is, here's just like a 1-digit object. This is a 2-digit. Bring down the 13x. Okay, so what do I have to do but multiply x by to get a -6x squared? Well, I'm going to need an x and a -6. So I'm going to put that in the x column, and I'm going to multiply everybody, and I'm going to subtract. So what was originally negative becomes positive. What was negative becomes positive. If I've done this correctly, the 6x squared should cancel. They do. So I'm left with a positive, excuse me, positive 18. It was originally negative, so now it becomes positive. And then this guy right here with this, so 18 minus 13 is my 5. If I've done this correctly, the x squared should have canceled. They do. Now I have a 1-digit object. I have a 2-digit object. I bring down the 15. So I ask myself the question, what do I have to multiply this guy by to get this? And obviously that's a 5. So I put the 5 up in the constant column. And then we go 5 times both of those. So I take 5 times x, I get a 5x. I take 5 times 3, which is 15. And then I subtract. This was originally positive, it becomes negative. This was positive, becomes negative. And notice everything cancels. And that tells me that this times this is this with a remainder of 0. Which means I factored this guy out. Now I'm going to take this and I'm going to create a new polynomial called x squared minus 6x plus 5. So I found one root, one of the factors. Now I'm going to do it to this guy. So I call it a different polynomial. And from our picture previously, we now have a new polynomial, and it looks like there's a crossing point at 1 and at 5. That's not a proof. So let's try it. So if by observation, it looks to me like one of the places where it crosses is at 5. I just chose that one. So let's put 5 into my new polynomial. Let's see what happens. So I get 25 minus 30 plus 5. So 25 and 5 is 30 minus 30. I get a 0. What does this fundamental theorem of algebra say? X minus a 5 is a factor of this guy. Which means when I take this into this, I should get a remainder of 0. And let's see if that's true. So what number do I have to multiply x by to give me an x squared? Well, it has to be x. Put it in the x column. So x times x is x squared. X times the negative 5 is negative 5x. Subtract. So what was originally positive becomes negative. What was negative becomes positive. These guys cancel. And plus 5 minus 6 is a minus x. This is a one-digit object. I have a two-digit object. I bring down the 5. And I subtract. So this times negative x gives me a negative x. Minus 1 times minus 5 is a positive 5. Subtract. And you get remainder of 0. What does this mean? It means this can be written as this times this with a remainder of 0. In other words, this divides into this. There's no remainder. So what that means now is if I put all this stuff together, I have this factored into here. Now, why are we doing this? Well, you're going to see this coming up in your homework problems repeatedly. Let's take a look at this, the top and the bottom. Now, is there a troublemaker? Yeah, you always look in the denominator, ask yourself the question, does that become 0? If it does, you've got a problem. And notice that if I substitute a 5 in here, I get a 0. But I showed previously, a couple pages back, that when I put a 5 in here, I also get a 0. So that means there may be some kind of a cancellation going on. And first, you have 0 over 0, which is indeterminate. So if I use the tabular method, what we do is we pick numbers to the left and to the right of 5. So I take 4.9, 4.99, 4.999, 5.1, 5.01, 5.001. And so I'm coming in from the left and the right. And it looks like these numbers are approaching, what, 32. And from this side, it looks like they're approaching 32. So this is by the tabular method. Now let's go to the division method. So what we've done is we've taken 15 minutes just to factor this guy right here. And we have x plus 3, x minus 1, and x plus 5. Now notice the troublemaker, excuse me, x minus 5. The troublemaker was the bottom. Notice that they, what, cancel. And I don't have a problem anymore. Which means if I take the limit of this new thing right here, now notice I can put any number I want in for x and here, and there's no problems with the evaluation. So if I take x plus 3, I put in a 5, I get 5 plus 3, that's where this comes in. I get 5 minus 1, which is this, and I get 8 times 4, which is what? 32, which is what we saw up here. So the reason I'm going through this is when you get to your homework problems and you try to do your limits, you're going to have some difficulties, and you're going to have 0 over zeros, and that means you have to do this long division stuff. Okay, so for problem number 26, let me just pause this for a second. Okay, now another type of problem that you're going to run into in your homework is things with square roots. So for problem number 26, I've got a fraction basically. And I claim that we have a problem if x is 9, which is something we're interested in. So if I was to put in a 9 here, I get 9 minus 9, which is 0, which is not good. And if I put 9 in the numerator, the square root of 9 is 3. 3 minus 3 is also 0. So what we find is this indeterminate form showing up again. And remember, 0 over 0 sometimes can be 0, it could be 1, it could be infinity, whatever. We don't know. So we're going to have to do some algebra. This is not, excuse me. So we're going to have to do some algebra to get rid of that 0 over 0, that indeterminate form. So here's what we do. There's an operation, and I want you to remember from Math 143, Finite Math, when you were working with matrices, and specifically when you were working with the linear programming problems, and you were going from the profit to the cost problem or back and forth, I want you to recall that you made up a matrix, and you took its transpose. And the transpose was whatever that was the row becomes a column. And if you took the transpose again, you get back to the same thing that you started from. Well, that property is something we call the conjugate. So if I have Wilma minus Fred, and I take the complement of this, I make this into Wilma plus Fred. So this was a negative, now it becomes a positive. If I take the conjugate operation of Wilma plus Fred, the plus becomes a minus, excuse me, the plus becomes a, the minus becomes a plus, and then if I go motorcycle plus pizza, and I take the conjugate, the plus becomes a negative. So the conjugate of two objects is, if this was a negative, it now becomes positive. If this was positive, it becomes negative. And this turns out to be a very important trick. Actually, no, it's not a trick, it's a property. So, so if I take the conjugate of a box plus a triangle, we change the positive in front of the triangle to a negative. If I had a negative here, I make it into a positive. Okay, so here's what I'm going to do. I'm going to have to somehow get this out of the picture. So here's what I do. I take the top, and I take the conjugate of this. So in other words, the conjugate is going to be square root of x plus a 3. So I'm going to multiply by 1. This guy is the square root of x plus 3 times the square root of x plus 3. Now we are going to do long multiplication. I'm going to take this times this. Let's do it. So I'm going to do this individually. So I'm just going to take the numerator, square root of x minus 3, square root of x plus 3, and I'm going to do my long multiplication. There it is. So I put the constants in one, then the square roots in another. So now I start my long multiplication. So this times this is going to give me a negative 9. This times this is going to give me a negative 3 squared of x. So I've multiplied this guy by everybody. Now I'm going to take the square root of x and multiply it by everybody. So this times this is a 3 square root of x. Put it in the square root column. Square root of x times square root of x is just going to be what? Square root of x squared, but that's just going to be x. So add things up. It should be just x minus 1. Okay, good. So upstairs, the square root of x squared is just x. These guys cancel, and I'm left with a 9 minus 9. So all I did was I multiplied these two guys here, and I end up with x minus 9. Okay? So that's very nice, because so when I just took the numerator and I multiplied, I get an x minus a 9. And notice what happens is the x minus 9's cancel. I don't want you to think of it as the x canceling the x. It's this whole object cancels this whole object. And so now I'm left with 1 over the square root of x plus 3. Notice I'm not dividing by 0 anymore, because we're interested in that 9. So the troublemaker, the 0 over 0, has gone, and I'm just left with this. So now, what this is saying is, so all this is algebra. This is not calculus yet. So by that conjugate stuff, I've been able to cancel the x minus 9's, and now I'm interested in what happens if I put in a 9 here. No more problems. Square root of 9 is 3. 3 plus 3 is 6. So we're guessing that the limit is going to be 1 over 6. Well, this is actually not a guess. This is correct. And we could verify this by doing the following. Go back to your tabular method. And the troublemaker was where? At x equals 9. So I'm going to approach 9 from the right and from the left. And so you just put those numbers in to here and do the arithmetic. And notice, because I'm not actually at 9, you'll be able to cancel things. So if you put all that into your table, so I'm going to come in from the right and from the left, it appears that coming in from the right, it looks like it's a 0.16 repeated. And from the left, it looks like it's 0.16 repeated. And in fact, if you take 1 divided by 6, you do get 0.16. Okay, so now you should have enough tools to do your section 1.5 homework.